There we go.
All right.
All right.
Yeah.
That was a good 10 minutes of everyone's time. Excellent.
I'll still share the screen.
Good. All right, everyone.
Yeah, please, please.
Everyone happy. Excellent.
Right.
Okay.
Okay. Okay, so we're starting perfectly on time. No technological issues whatsoever. So we're very happy to have Cari Cesarotti here today from MIT, and she's going to tell us about Future Muon Collider. So thanks, Cari.
Yeah, so hi everyone. Thanks so much for having me. And thanks for bearing with me these past 5 minutes. So today I'm going to be talking about the possibility of a future collider, which is a muon collider. Before we get started, I want to emphatically say that this is not a strict endorsement. I think that having any sort of future collider would be an amazing investment for the field. And this is just one possible option. So as physicists, it should be our responsibility to explore the full physics potential of these machines before committing to them. And this is just the summary of one particular machine. So all right, great. So given that this is such a long, expensive process, the first question you should naturally ask when someone tries to sell you on a future collider is, why do we need another collider? And really, there's a lot of reasons that we should still be investing in collider infrastructure. So there are a lot of unanswered questions that we still have in particle physics, not only for the standard model, but also beyond. So in the standard model, we have a lot of questions that we don't really fully understand. The Higgs boson was discovered, but there's still a lot of mystery that kind of comes along with it. Why does it have its mass? Why is it the only light scalar? Is it composite? Things like that. Going along with that, we have questions about electroweak symmetry breaking. We expect that we understand that mechanism, but since we haven't really gone well above the hundreds of GeV energy scale, there's still some uncertainty. And then there's some other just bigger questions that we have in general, which is what about the baryon asymmetry of the universe? Where does that come from? Leptogenesis? What is the origin of flavor? Things like that. So there's still a lot of open questions. Okay. And then if you want to think about questions beyond the standard model, so things that we still need to answer, but don't have as clear of a picture about perhaps, is what is the particle content of dark matter? Something we haven't been able to understand. What exists above the 10 TeV scale? Are there other hidden sectors that could be weakly connected to the standard model? And what is the source of anomalies that we're still seeing? So even though anomalies come and go, certainly some have persisted, and we should understand the fundamental nature. Right, so we're at this interesting junction in particle physics where we sort of need some experimental or empirical input because we don't have one clear beacon of a theory that would answer all of these questions. So collecting the data to inform how we approach these problems is something very important to the field. All right, so given that paradigm, the experimental program that might be the most lucrative in terms of making progress is something that might be able to do the most generically put new stuff. So when we think about colliders in the past, usually we talk about two kinds of machines, either something that can achieve high precision or something that can go to high energy and make a discovery. So previously, when we've talked about these two kinds of machines, we usually talk about E plus E minus machines like LEP for a precision machine. And for discovery, we talk about hadron-hadron like LHC, right? And we call this the precision machine because since there's no hadronic backgrounds to our collisions, they have roughly kind of clean signatures, and we can reach high statistics with these. So since we're doing low energy things here, usually this will just provide a hint of the UV completion. So this is a very EFT approach about studying things with precision. Whereas for discovery, since we're able to just reach these higher center of mass energies, we can actually have on-shell production of new degrees of freedom and then make some discovery. And so this can tell us what the origin is. And these machines, of course, have to work together historically, because whenever you have a hint of what happens in the UV, you can only confirm by actually going all the way up there. All right, so when we're thinking about the paradigm of what do we need in particle physics next, it would be really amazing if we could have something that could do both. And so this is one of the most compelling reasons that we should consider a muon collider, is because it is a machine that allows us to use not only precision, but also a discovery portal for particle physics. All right, so I want to give you some timescales of how these future colliders can be done. And as I insinuate here, you should take this with many grains of salt, okay? So sort of what we expect in the next few decades of what we'll get out of experiments is stuff pertaining to the LHC. So we're going to be running run 3 for a little bit longer. We just started. And then we have the high Lumi upgrades, which will likely spill into the 2040s in some capacity. These are basically guaranteed to have this stuff. right? Then there's discussion of having an E plus E minus linear machine that could run at the Higgs resonance. And so we could maybe do some Higgs physics. There's a lot of discussion about machines like that. It is unclear to me how on shell these proposals are. This may or may not happen. So then the other biggest high energy machines that people probably talk about is the idea of the Future Circular Collider, which would likely be sited at CERN. So there are two stages to this. One is the FCC-EE, so it's colliding E plus E minus. And then another is the FCC-HH, which is again protons like the LHC. This machine has the benefit that we basically know how to do it. But as you can see, there might be some large delays in being able to actually construct this machine. So Muon Collider, again, a very uncertain technology, but if we were able to actually pull it off, we could have a machine that's functioning at 3 and 10 TeV center of mass, hopefully in the next upcoming decades. So the fact that we can get these higher center of mass energies is probably one of the biggest compelling reasons to be able to do this Muon Collider. So then if you're going to ask how on earth do we achieve this never before seen thing in the next couple of decades, that's a wonderful question. And here's what the experts suggest. Basically, what we're considering as the biggest things to work on is the acceleration. Is definitely the most uncertain piece of technology. So here's, a bunch of words that tell you roughly when things happen. But the thing that's going to be hardest is basically demonstrating this cooling, and I'll talk about it more. But the thing that's hard, of course, is producing muons and then accelerating them before they decay. And that's where a majority of the challenges will come. But assuming that we can follow a rough timescale like this, and again, this is technically limited, so not something that's on shell with funding or anything like that. But if we can sort of follow this rough timescale, then maybe in the 2050s, likely end of 2050s or so, maybe 60s, we might be able to see the 10 TeV frontier. All right. So when we talk about the Muon Collider, oftentimes people will present you with a bunch of different energies as staging options. So of course, sort of this 10 TeV number is sort of the nominal benchmark of what it means to really surpass the energies reached at the LHC. But often you'll see these other sort of benchmarks as staging options, and I want to explain where they come from. So basically the idea of staging something like a Muon Collider is to ensure that you're still getting a physics program out of this machine, even if there's unforeseen technical difficulties. So given that this is such a risky thing to do, it's important to have sort of backup plans to make sure that if something fails, there's still a physics program. So 3 TeV is interesting. One, because it's kind of the first thing that we haven't seen with the LHC, is we've made very precise measurements, sort of up to 3 TeV, but we haven't been able to push too far past it. And it's also kind of an indication, if you take this EFT approach, of where there might be some new physics, because this 4 pi times the BeV is roughly at that 3 TeV. So again, this is sort of the first place that new physics might be able to show up in a way that's consistent with our previous expectations. This 10 TeV number is interesting, of course, because it's unforeseen energy frontier, but also we start to see some new standard model phenomena that wouldn't have been able to appear before. So one of the things that we haven't seen is having something like electroweak jets, where your very energetic particle is radiating things like Z's and W's instead of just photons, in the same way that an energetic quark might radiate gluons. So roughly, you start to have this emission happening with some sort of actual frequency when this energy hits about 10 TeV. So then you can start to observe this phenomena that we expect to happen, but haven't confirmed. Right? And then these big numbers, the 30 TeV, 100 TeV, there's some physics motivation about, testing dark matter thermal target candidates. But really, it's just kind of exciting as the most dramatic new energy frontier. And this 100 TeV number is sort of the limit on reasonable projections, where you would kind of start to really need a completely new paradigm of how to accelerate particles beyond what we think is possible. So this is kind of that explanation. All right. So given all that, now that I've caveated that this is hard, what exactly is hard about it? And I think it can all be simplified by the statement that muons decay. And the fact that muons decay on the microsecond timescale presents a lot of interesting problems. So a tau collider will never happen, right? Because that's another 7 orders of magnitude quicker decay. But with microseconds, we might have a chance. So the first problem with the fact that muons decay means that, of course, there are no muons found in nature. So in order to have a muon beam, you have to first produce them. and then accelerate them before your whole beam is decayed away. So when you produce them, the mechanism that we use so far, we have protons incoming on some high Z target that produces a bunch of mesons like pions, and then pions decay into muons and neutrinos, and then those muons are scooped off to be accelerated. Right, so when this is happening, because this is a tertiary particle, whatever collimation you had in this initial beam has, of course, dispersed. So the spread in momentum longitudinally versus laterally is like order 1. So these are really diffuse in phase space and you need to refocus them. Right, so then that act of refocusing them, which we often call cooling or 6D cooling for the 6 dimensions of phase space, needs to happen quite quickly and needs to be quite dramatic. So when we have these muons coming out, roughly the size of the muon beam is like this. And if you do collider physics, you know that that will have 0 luminosity. So what needs to happen is about a factor of 1,000,000 reduction in phase space. The best technology that we have that can hopefully do this is this process of basically running your beam through material and then squeezing it with a magnet. So Liouville's theorem tells you that you can't just squeeze it and constrain it, right? You have to actually have some lossy process to make sure that you're reducing the phase space. So run it through material, it loses some momentum, you tighten it back up, repeat that, roughly 120 times will then give you that 10 to the minus 6 reduction in phase space that you need. So this has not been demonstrated, and this is kind of the most outstanding and expensive part of the process. Okay, and then
They really need 100 cycles, or I thought there was one more.
was more.
No.
Oh, yeah, basically they're projecting that you would have 10% loss every time. And then for a beam this big, to get down to like 100 MeV energy in the right cross section, it's the 120.
You recycle some of this, so your things, your cooling stages, are they like repeated, or
Yeah,
you have to have?
The idea is that it's 100 cells back to back to back to back. Yeah.
There's no turning back, it's one shot.
Yeah. Or muon shot. Okay. But yeah, so this is what needs to be shown absolutely, right?
What's shown is already the 10% phase space reduction.
Yeah.
Nice.
So
Could they achieve better reduction, 20.8?
So I think roughly like what Jen is saying is that there was a collaboration called MICE, which was the muonization cooling experiment, and they were able to show this roughly 10% loss every time it went through a material. What hasn't been shown, so they did it with 1 muon at a time. So what hasn't been shown if there's any like effects from having a whole bunch and doing it repeatedly that wasn't accounted for before. So yeah, simulation is promising, but we haven't actualized anything like that yet. Okay. And then of course, finally, acceleration is a challenge. At the LHC, it takes about 15 minutes to accelerate protons up to their full center of mass energy. We don't have that kind of time. So developing an accelerator lattice that's not a bunch of magnets together, but instead one magnetic field with a very quick injection is going to be a very different acceleration challenge for the particles.
So you said like a big part of the problem is this microsecond lifetime.
Yeah.
For the acceleration part,
Yeah.
you at least win a little bit because of time dilation.
Yeah.
You get a little bit more time.
Yeah, absolutely. So these are not very relativistic muons coming in, like gamma is like 2 or something. So this is the really dangerous decay process. And then the fact that, just as you say, because you have a huge gamma factor here, that means that you can actually, once you get them up to speed, you can cycle them like 100 times or something before your beams decayed away substantially. So yeah, it's this part that's really the thing that's tricky about the short lifetime.
Okay, the 6D cooling, you don't get any gamma factor.
Yeah, it's basically non-relativistic. Yeah. Okay. So then one other challenge that comes with the decay is basically dealing with the fact that you have a decaying beam with your detector. So if you have muons incoming, you're also producing electrons and neutrinos at very high energy, and even neutrinos start to interact when you have order TeV scale energy of these particles. So one of the things that our experimental colleagues have to deal with the most is called this beam-induced background, which is basically all of this shrapnel coming off of the decay of the beam instead of your hadronic background enters your detector, and you have to find a way to cut out that from your interesting physics. So they have ideas about timing and energy cuts and things like that that can reduce it. But making sure that you don't just have beam decay products as the dominant thing you're detecting is an active challenge. And then something that's kind of a surprising challenge is the fact that now you have a huge flux of neutrinos coming out of your experiment everywhere, because everywhere you have neutrinos decaying, not just in your detector. So making sure that we're not giving the land around the Muon Collider a lethal dose of neutrinos is important. I'd like to say right now that basically it is always below the legal limits at surface level. So this is not a dangerous thing, but it is something that we have to be absolutely, completely sure about is safe before we could proceed. Okay, so we've been talking about Muon colliders since the 90s. What's happened recently to make this seem like a more feasible option? Like Jen mentioned earlier, there's been a lot of progress with the cooling. So with this MICE collaboration, they've been doing some simulations and testing, and they find that you can probably do it. But again, there's no concrete evidence until we actually build it. Right? There's been a big development in magnet technology, which again is important for having that very high stable field inside the actual acceleration. And there's still some things to be done here, but we're making good enough progress that we feel confident to proceed. And a lot of these things would overlap with what we need for the FCC as well. And of course, there's community interest. So why build a giant machine if no one cares about it? It seems like there's a big resurgence in people actually wanting this machine, which is, of course, the primary thing that's going to actually get it completed. So we have a collaboration forming in the US, and in Europe, they have an international Muon Collider collaboration that actually has roughly $10 million a year to contribute to this. Right. So last time we talked about it at P5, they were saying, oh, we need N miracles, where N is a big number. And now how we're talking about it is there are no showstoppers identified. So really, given that some of these big scientific funding agencies are asking how should we spend our money, we should be very clear that the time is now to think about investing in this future collider. But of course, it needs R&D, but R&D needs money. So it's all kind of this insane loop of weird feedback. But if this is a feasible technology, it could really be an amazing breakthrough in particle physics, even in the next few decades. So I talked about Muon colliders. How does this compare to other colliders? We can just consider sort of these broad categories of proton machines, Muon colliders, and E plus E minus. So because proton colliders collide composite particles, you lose a lot of the energy in the center of mass due to the PDFs, right? The partons are only carrying a small fraction. Whereas at lepton colliders, basically, the particles are carrying all of the energy except when they're radiating gauge bosons, which is also useful, and we'll talk about that in a second. But this is why your 14 TeV LHC is comparable to something like a 3 TeV Muon collider. So the improvement of energy reach is roughly a factor of 10 in terms of leptons versus hadrons. Right? Why can't we just do this with electrons? It seems like it would be much easier since they don't decay. The problem is synchrotron radiation. So synchrotron radiation, if you remember from E&M, scales as gamma to the 4, which is the energy over the mass. So for the same energy, given that these two particles have such dramatically different masses, you'd radiate 1 billion times more energy trying to accelerate E plus E minus in a circle rather than muons. So that's why it's only really feasible to achieve, again, up to maybe this 100 TeV number with muons. Right? In terms of the physics that you're actually studying, the kinds of processes that are dominant at P plus P minus, my goodness, at proton-proton machines is QCD, or things that are mediated, of course, by gluons, so gluon fusion processes. Whereas at Muon colliders, whenever you don't have that full center mass energy, it's because you're radiating off W's and Z's and things like that. So this provides a lot more room to study things like electroweak processes. Right? And then just overall, what kind of physics content are we really probing? Because of the PDFs, again, you're primarily seeing first generation particles in PP machines, and in E plus E minus, that's certainly true as well. So this would be really one of the first probes that we have of a very clean, repeatable way to study second generation particles. But of course, to be fully honest, these things aren't strictly true. We still see very high energy collisions in hadrons, and we can still probe second and third generation things with proton-proton. So it's not uniformly correct, but it is a good approximation.
Is there a reason why you're talking about mu plus mu minus as opposed to like mu plus mu plus?
Great question. So at JPark or at Keck, KEK, if you want to call it that, in Japan. They actually are talking about doing a mu plus mu plus. And so that's a really interesting idea because this doesn't matter if you're doing mu plus or mu minus, you can still be producing gauge bosons. So if you're really interested in just scattering gauge bosons with a lepton or other gauge bosons, mu plus is much better because mu pluses are easier to produce than mu minuses. So great question, but if you want that S channel annihilation, you have to do mu plus mu minus.
Oh, okay, like if you wanted to do like a Higgs factor.
Just anything that has, an annihilation process to get the full center mass energy. Otherwise, you're basically functioning at a much lower center mass energy. Yeah, good question. Okay, so here's kind of the schematic that we would hope to see. You have a pretty low energy proton injector, so it makes sense to do this at a lab that already exists, like Fermilab or CERN. You accelerate your ring, or you accelerate your particles in a ring, and you collide them in a ring, and you expect it to go around roughly 100 times or so per bunch before your beam has primarily decayed. Okay. So then something that's really notable about this machine's layout is that it would be much more compact than other experiments. So with the FCC model, they're talking about doing a 100-kilometer ring, whereas we would be talking about doing something like a 10-kilometer ring. So the fact that this has much less land to excavate is an amazing, not only environmental save, but also potentially money save and technological save, because I don't know if you remember. This is circumference, 10-kilometer. Yeah. But yeah, the LHC like hit an underground pool and then it stalled building for 6 months. So these things matter when you have less uncertainty and having a huge footprint. Okay. And then of course, a natural question should be too, if you have leptons, why not just do a linear collider instead of circular collider that you can use electrons? So again, going back to this idea of just what is feasible to do with human technology, you need to have your luminosity keep up with energy squared to make sure that these S-channel processes are not completely dying off as you go to higher energies. So if you assume that this is how your luminosity has to scale, basically the luminosity for power delivered for linear machines doesn't have anywhere near as much return for circular machines. So the more that you accelerate for muon collider, because muons live longer, you actually get more luminosity out of it. So in terms of that environmental impact reason as well, doing a circular machine would be desirable. Okay, so that's all the technology behind it. Now let's talk about the fun stuff, which is what sort of physics you would hope to be able to do with this kind of machine. All right. So just to give you kind of a broad summary of what kind of things you can hope to study, we can break this up into, again, these two categories of either sort of standard model-y questions that we know we can answer, and sort of dreamer questions that we hope we'd be able to answer, but of course are no guarantee. All right, so in the electroweak sector, we want to study things like Higgs production, Higgs coupling, and VBF functions in general. This is something that, again, a muon collider in particular can excel at as a high energy machine. And then on the other side for new physics, basically any sort of thing that you have where you're producing very heavy new states, so things above the TeV scale, things that couple more strongly to these heavy flavors. So if you're coupling more strongly to second and third generation, which is anything that sort of follows that minimal flavor violation extension of a standard model, then that would be something easy to study with the muon collider. And then of course, there's this idea that if you have a high energy machine, you get precision out of it as well. So these two things kind of talk to each other with this EFT framework and how you get these low energy effects from the high energy phenomena. All right, so let's talk about some concrete examples. So first, let's talk about the sort of Higgs physics that you can do. So the way that you're producing Higgs is going to be very different at the proton-proton machines versus at the lepton machines. So again, already some motivation as to why this would be a complementary thing and not a replacement. So instead of doing this top loop, the primary way at muon colliders that you'll be producing it is with VBF. And again, this process grows logarithmically with energy squared. So the higher energy machine you have, the more Higgs you're producing. Right? And that's not quite true for E plus E minus machines. One of the stages that we proposed for the FCC-EE is not actually at Higgs resonance because the top you cows. the electron Yukawas are so small that doing it at resonance there was not the best way to actually get Higgs production. Instead, the most Higgs production will come from this radiative Higgs process. So this is happening at this 240 GeV number. And this is something that they would do to make these Higgs factory runs at the FCCEE. Okay, so you can see that a P plus Q minus machine basically. No, P plus, sorry, I don't know how that ended up there. Your brain just really auto-completes sometimes, okay. So when you have your PP machine, you can see the cross sections are a factor of like 1,000 bigger than what we can achieve. But again, given the monstrous hadronic backgrounds that you have, there's a lot of channels with which you can't actually find the Higgs anyways. So the sensitivity drops it way back down, and it becomes kind of a compatible measurement region again. For a muon collider, just kind of highlighting these regions where we have benchmark energies that we want to study. We see that we're producing mainly again for this fusion process, but yeah, producing ultimately like 10 to the 6 Higgs, even at around 3 TeV. Okay, then at E plus E minus, again, you have the process dominated down here is this process, and it's producing again roughly 1 million Higgs is what we would expect. So if you want to think about going to energies all the way up to 30 TeV, then you can kind of start scraping close to that number of 10 to the 8 Higgs, and you can do really good precision with that. But otherwise, the kind of precision on couplings you expect to get is sort of 1% for the 3 TeV and sort of 0.1% for the 10 TeV or so. So producing, again, maybe more than 1 million Higgs, even with just a muon collider. Okay, so then we can sort of study exactly how that will work with the other Higgs couplings a little bit more generally. So this is work quoted by Mead and Forsland, where they've studied all of these different Higgs couplings in the Kappa framework. And you can see if you compare, these are the high energy options versus muon collider, is that there are definitely processes with which a muon collider is advantageous and processes in which having an FCC-HH would be a better strategy to find. So they're not going to, again, be probing the exact same things. They have sort of complementary sensitivity to these different couplings. And of course, that is all just a function of what is your final state? What are you sensitive to? What can your detector do realistically well? Yeah, and then here's just a nice summary of these statistics. So something else that I want to point out that I think is a very interesting challenge for muon collider is you have these 2 bars you can see where this is a darker shade than this. And the difference is basically if we're able to forward tag particles at our detector or not. So again, with this background, this beam-induced background, you're shooting a bunch of high energy particles very forward because they're all boosted from the headlight effect. And so it might be difficult to reconstruct particles seen in the forward direction. So if you don't have the ability to distinguish, it can really reduce our sensitivity. So this is one of the biggest problems that's important for experimentalists to address, is just how do we understand what's going on in this forward regime. But okay, yeah, as you can see, sort of sub% precision on a lot of these couplings.
So in fact, on this topic, it's critically important for muons, not best represented by this bar, because one feature of future E plus E minus machines are the ability to determine Higgs width and determine coupling strengths. Without forward muon tagging, I cannot do that at the muon.
Yeah.
Which we pointed out and to show people how precise you can do that. So
yeah.
They came out this last month.
Okay, sorry, everyone read Jen's paper about the Higgs width at muon colliders. Yeah, the forward tagging is definitely one of the biggest limitations to actually.
About this tiny improvement of factor 2 improvement in certain topics, about whether this handicapped assumption on no BSM decay can
Yeah.
be alleviated.
Okay, yeah, that's an important point. All right, so another aspect of Higgs physics that's important to understand, what does the Higgs potential actually look like? So we're always taught that we have this very well-defined idea of the wine bottle potential, but just given LHC measurements, this is how unconstrained the potential is, right? We've measured this parameter of the potential very well and everything else not quite as well. So all of these horrible geometries up there are consistent with the measurements we've made at the LHC so far. So once we do the high L LHC run, if we get the full run that we're expecting, a lot more is constrained. But to really constrain it much more, you need something that goes up to these very high energies as well to be able to produce these Higgs states on shell. So again, these are the processes that we're hoping to be able to study better with a muon collider. And again, having 3 on-shell Higgs in the final state is something only a very high energy machine can hope to do. So you can see that as long as we're doing sort of like this 10 TeV regime, the reach that we could get from the hadron machine is probably comparable. But as we go to higher and higher energies, the precision on this diagram in particular gets quite strong, and we're able to constrain the potential much better. So going to Zhen's point again, something that's so important that we understand is actually how much reach we have in that forward regime. So this is, I think, done using Higgs to 4B final states. And of course, this process is going to be a very forward process. This is a vector boson fusion process. So something that helps us understand the sensitivity and understand more concretely what this reach could be is the fact that this production is kind of central in your detector. It doesn't have a lot of pileup on the edges of the detector, which means that it's a more reliable projection to make. It doesn't depend as strongly as reconstructing the events that happen very forward and very backward. All right, so doing these kind of studies is something that's going to be imperative to actually knowing what our sensitivity will be before we have to construct the whole thing. All right, so that was a very quick, of course, there's many more things to do with the Higgs, but that was some ideas of what we can do with standard model physics. And now let's think about how we can use it to sort of generically study new physics scenarios as well. Okay, so again, if we just want to take this very bread and butter model of how new physics looks, is we're just doing some S-channel production, and that's how we get all the energy out of our collider. We need, again, some process that looks like this. And here's just a couple benchmark scenarios using SUSY as the toolkit. So here's just some super partners that we could be hoping to produce. And again, we see something not so surprising. So if we have so this is for a 10 TeV collider. So since we're doing pair production in the final state with this kind of thing, sort of the kinematic threshold is going to be at this square root of S/2 stage. So we expect the production beyond that to drop to 0. And you can see that, it sort of levels off in this intermediate here where you're not losing things to this kinematic threshold. And we're able to produce like 10 to the 4, 10 to the 5 of these new physics. So of course, exactly what sensitivity you have depends on your background control. But we would hope that this could be enough for a couple sigma discovery of these kind of phenomena. Okay, so here's a little bit more concrete of a model to consider instead of just SUSY. So we can consider something that has sort of a Higgs mixing portal. Of course, yeah, heavy scalars want to mix, so why not let them? So basically, this is the kind of 2 diagrams that we're considering. You either have this angle gamma, which represents how much these scalars mix. And then this would be how you could study this at the LHC with this effective top loop integrated out. And then at, again, lepton colliders, if you're doing this, it's going to be producing a Higgs through this vector boson fusion process. So here's your generic model, 2 scalars mix. Right. And then, of course, a lot of these things will depend on your final state, but we can look at what the reach of these things should be as a function of what sort of energy the scalar is and this mixing angle. So these straight dashed lines come from the fact that you're just producing something, like this diagram here. So it's not going to be a function of sign. This is the Higgs in the intermediate, so it's just going to be the Higgs doesn't matter the mass of the other guy. So it's just constant in angle there. But yeah, you can see that having this sort of diagram, because again, you have this vector boson fusion process and it's not happening at the full center of mass, you have more sensitivity sort of down in the lower masses, but it persists and it is competitive with something like the FCC up to pretty high energies as well. So again, this is different muon collider energies, but for a big part of parameter space, they're comparable for much higher energy hadron colliders as well. Okay, and then here's just to give you sort of that same diagram, but emphasizing the muon collider contribution a bit more. You can really start to expand this reach as you go to higher and higher energies, because again, you're producing higher energy gauge bosons, and that allows you to probe the higher energy scalars as well. So yeah, you can really study quite a bit in terms of this new heavy scalar scenario with a muon collider. Right. Here's another sort of generic model that now that RK is not persisting anymore, we'll say it like that, is maybe not as talked about these days, but we can also think about some sort of leptoquark-like model. So there's a whole bunch of leptoquarks. Here's one specific representation that we have. And you have basically, we're considering only the left-handed couplings. So to integrate out all of the whatever about it, the important points are you have some new spin 1 vector boson that couples two quarks and leptons. And then the exact structure of the flavor and how they couple are sort of up to the model builder's choice. But we'll consider basically that these things are primarily interacting with second and third generation stuff because first generation is suppressed by the heavy flavor and would have been seen at something like LEP. So if you have something that interacts with quarks and leptons, mainly at second and third generations, a muon collider is really the best place to be looking for something like that. Okay, so if U1 here is our new boson that our new leptoquark that we're producing, these are sort of all the diagrams in which you can produce it. So yeah, just to give you kind of an overview. So if I want to translate that into bounds, we can consider, so we consider specifically for this a 3 TeV muon collider. And then these different lines come from these different diagrams roughly. Again, when you're doing this pair production, this axis is the coupling to the quarks and leptons in specific. And when you're producing it like this, it's mainly just coupling to gauge bosons. So again, in the low energy, you're always talking about new physics coupling to gauge bosons. And at higher energy is when you have this more like bond shell production that's talking to the actual partons that you're accelerating. So yeah, again, maybe not as exciting now that RK is no longer an anomaly that persists. But again, being able to study something in the many TeV range was sort of specifically coupled to second and third generation is something that a hadron collider couldn't do with this kind of precision. Okay, one more model that I want to give you is an idea of doing some sort of WIMP dark matter consideration. So WIMP dark matter is particularly compelling because, as the W would suggest, it couples to the weak force, right? So the kind of process that we're interested in is studying standard model particles come in, are mediated by W, and then we have dark matter final states.
Your dark matter then is charged.
So I'll get there. Yes. In this case, it would be charged. But okay, I'll ruin the punchline. So if you have something that's charged, you can have it radiate off something that's charged and then have like a disappearing track kind of state. So you have like a light pion that gets spun in and then this becomes a chi0 and then that's your dark matter candidate.
Friends of dark matter.
In a multiplet where the lightest uncharged state would be the dark matter candidate, yes. Yeah, so the authors of this work and then a couple of other follow-up things too, what they consider is just some n-plit under electroweak. And then the neutral thing will also be the lightest thing. You can think about that like pions, right? The chi0 is the lightest and you get contribution from the mass of charged particles and loops. So whenever you have some n-plit electroweak set, the lightest thing will also be neutral. And if you have a production like this, you can always have some sort of process where you decay off something like a pion, you lose a track, and then you have a chi0 in your final state.
So if the interest is like plus and mass, then you also don't have this process, right? So you're kind of thinking about eliminating particle.
Yeah, so I mean, okay, I'm sorry. This is mainly just to illustrate the fact that it's dark matter. But yeah, you would also be having things that are produced with like this vector boson fusion kind of stuff as well.
Put a C there.
You could also put a Z there. Yeah.
But then no C. What do you mean?
Well, dark matter missing energy.
No, but you can then produce the charge, you can produce the chi plus and chi minus, which decay into the.
Oh, yeah.
Yeah.
Too.
Yeah.
That's hard match, right? The easiest channel is smaller photon.
Yeah. So yeah, this is just supposed to give you WIMP vibes, not exactly at muon collider. But yeah, okay. So if you have this as your model, just by knowing the relative abundance, the freeze-out abundance, you can calculate what the mass would need to be if this is the representation of your multiplet. So it's a well-defined question. And so basically the question is, given exactly what your search strategy is, mono photon, mono X, whatever, can you reach sensitivity at the desired energy with a muon collider is what they explore in this paper.
Are any of these candidates already ruled out by direct assessment?
I think for the higher multiplets, I mean, so like if you just want pure Higgsino stuff, like clearly there's better constraints. When you start getting up to like the 5 and 7 multiplets or something, then there's a lot less constraints that have happened. Yeah, okay, so like Shen was saying, there's a bunch of different search strategies that you can employ, and then exactly how it's produced and then what your signals are will vary for these different channels. But basically what's interesting to consider is that if you have something like a little over a 10 TeV, a 14 TeV instead, muon collider, and you have a 3-plet of this electroweak state, is that you can actually reach what the thermal target should be. So because you have these very high energy, weak particle collisions, you can actually hope to exclude some of the thermal targets for these almost minimal dark matter models, which is a really compelling reason to want to study this, I think. Okay, so then I just want to say some lightning fast things about how you could use indirect production of new physics as a means of studying things in a muon collider as well. So with the EFT approach, you're kind of exchanging having high energy for precision, but you don't have necessarily the confidence that your operator is generated by a certain set of physics, right? So if we just consider you have some Lagrangian, you have some dimension 6 operator, you expect this to be roughly what your theory would look like. Okay, so then let's assume that you can make a measurement of some, I apologize, observable and operator look the same. We can measure some observable to 1% precision. And then what that tells you is that, you know, given this sort of dimension 6 operator, is that the precision will look like the energy squared over the new physics scale squared, right? So if you're getting 1% precision measurement on some observable, then if you're making this measurement at 10 TeV, then the energy scale, which could be generating this effect, is already at 100 TeV. So again, it's not a precise measurement that tells you exactly what the underlying phenomena is, but it tells you roughly at what scale you expect this new physics to show up. So this is part of that hint versus discovery picture that I presented in the beginning. So even though you're only looking at 10 TeV, you can still be sensitive to much higher energies. And so this could provide, you know, a bigger clue perhaps about what future collider to do even after that. So then here's some thoughts. I'm not going to give any sort of justice to explaining. Basically, if you do sort of these fits on these universal theories of operators, you can use this to extract what kind of precision you would be able to get with a muon collider. So the green bars are muon colliders, and then of course having high Lumi and muon colliders at highest energy is what's going to give you these red bars, and that gives you the most precision on any of these operators. So having more precise operators is a better hint about where high energy new physics could be hiding. And that's just a nice thing that we can do when you have energy frontier machines. Okay. So the last thing that I want to say is that maybe I've discouraged you by showing you how far in the future all of these things have to happen. And you're saying, well, I want new physics right now. I want to discover things right now. Same. But maybe there's some other ways that we can utilize the necessary R&D program in order to have that full-fledged muon collider, and instead run some earlier auxiliary experiments that go along with the R&D that would be required anyways. So the last thing I want to just entice you with, since I am super out of time, is what sort of parallel opportunities could exist just by doing the necessary research to see if this machine is even feasible. Okay, so if we want to think about sort of the region of parameter space where new physics could be hiding and what we're sensitive to, with the colliders, we're going to be blocking off sort of this area where we can go up to that TeV range, but we don't have infinitely small precision or be able to test really weakly coupled stuff, right? Historically, how we've been able to sort of conquer this intermediate regime where we have MEV to GeV masses at much weaker couplings is with beam dump experiments, because you have you lose some energy because you're colliding with things at rest, but the fact that you're dumping onto something that's got 10 to the 6 particles in it means that you gain a lot in terms of weak couplings. So if we were to do this with a full collider, of course, the start date of these type of experiments would be a couple decades away. But the idea is that, you'll be having sort of these intermediate steps where you might have some sort of collimated or intense muon beam. And maybe you can start sort of carving away new interesting spaces to look just in that stepping stone in constructing the actual muon collider.
But is there a reason why the beam depth goes like this? I would have thought it, like based on the argument you gave a couple slides ago, I would have thought like at lower energies you have more sensitivity.
Yeah, so you don't have infinitely low. So yeah, the problem is that the coupling and the lifetimes are tied together. So as you go to lower and lower couplings, not only are you producing it less, but the ones you produce it have longer lifetime. So then they can live long enough to escape your experiment as well. So kind of the shape, this is a cartoon because they don't have the the right tools to draw it, but it's really kind of, you're right that it's definitely less steep than this, is kind of how it goes, but you do start losing sensitivity at low energies just because, yeah, things like live long and you're not producing as many and that kind of thing. But yeah, I'll show some more plots and let me know if you're still not believing the story. Okay, so here's just some sort of benchmarks that we might have to achieve, things that would go along with the program and not be a dedicated study anyways. So just producing the muons means that you have sort of this sub-GeV muons, and then cooling them gets you like hundreds of MeV. If you're accelerating the muons, but not all the way up to the full thing, maybe you have order of tens of GeV, something that's kind of a relic of the past, because again, this isn't the best way to be producing Higgs at muon colliders. Maybe you can have a Higgs factory, then each muon is carrying roughly the 60 GeV number. And then if you're going all the way up that sort of actual collider scale, then you have the beams that you'll be dumping anyways, because once they decay too much, you don't have very good luminosity anymore. So here are some things that could happen just naturally in the process of building a muon collider. All right, so given that we have the muon beam, let's see what kind of physics we can get out of it. Doing beam dump experiments are super easy in comparison to the full scale thing where you just have your beam is on some target, you have some shielding to get rid of anything else that comes out of it. So in theory, you just have some new particle that's propagating over a big length. And as long as it decays back to something visible, you can put a detector at the end of the hall and you can hope to see some sort of signal. Okay, so like we said, this can study both extremely weakly things and moderate energy. So not that full 10 TeV scale, certainly.
Just a nice question. So in this case, like how important it is to have a hypogeneity and like you mentioned on muon collider case, like improving this keep on mind.
Yeah, but the thing is, for this kind of experiment, you don't necessarily even need a very collimated muon beam. If you have some sort of tracking that happens at some point here, you can reconstruct the vertex and then, yeah, so that's a nice thing, is that you don't need a very tight beam. And in fact, by the time you're dumping a beam, it's going to start diffusing anyways, because the max angle is like milliradians. So having a diffuse beam helps you not destroy your target, and it's not necessarily a problem for your sensitivity. So a diffuse beam is actually good. Okay, so just to give you like this idea of how many muons you lose in the process of trying to do this, if you just dump your protons onto a target and then you take your uncooled muons, by the time you put them into an experiment, you have maybe 1% of the total particle number ready to use. If you want to cool them, you lose another factor of 10, so sub 1%. And then if you want to accelerate them, again, we talked about this. This is the dangerous stage where things can decay. And once you start accelerating them, things don't decay quite as much. But still, you're talking about way less than a sub % of your original number of particles. So it's kind of this trade-off between, do you process it more and then lose your number of muons, or do you process it more and then have a better idea of what your signal should be? So toss up for physics optimization. But the point is that this can all run usually synergistically with either existing infrastructure at the lab. So like at Fermilab, they just have muon beams to use that they just throw into the ground because no one has anything to do with it. Or it can be just the beams that are getting dumped from the actual collider.
What are the percentage? Those are the waste muon flux you're going to use them for beam dump?
This is the amount of, so this is the relative fraction of the number of original particles on target that are available to be used. Yeah.
In principle, if you want the muon collider, I will go follow the line along the accelerator.
Yeah, right.
I don't want to lose any flux to do my collider.
Yeah,
So it cannot be concurrently running with them.
yeah, but the idea is that you would just dump the central beams rather than run it. So yeah, like the luminosity for muon collisions goes as the particle density per beam squared. So as things start decaying, you're really losing luminosity super fast. So I think it might be advantageous at some point to just dump the beams instead of keep circulating them, because you can't just continuously do injections. Yeah, so I agree. If you have their full muon beam, collide them, don't just dump them for the sake of dumping them. But if you already have the beam that needs to get dumped, might as well put a detector. That's the point, yeah. Okay, so then just to give you some projections, I know I'm out of time, sorry. Here's sort of the reach that we hope we could do with that full muon target. So again, if we're assuming that we already have the collider and we're just dumping the beam sometimes, I just want to highlight some features of these plots instead of explain them too much, because you have eyes, you can see that they go past the shaded region. Awesome. But the point is, for something like a dark photon, where coupling to a muon isn't particularly important, it's just the energy. So having higher energy means that you can boost things that would have usually been too short-lived to decay in the actual region of interest. Because you boost them, you give them a longer lifetime, and they can survive for longer. So that's why this whole curve kind of gets shifted to the right compared to some of the existing things. So the reach for something like a dark photon is just having more energy means you can probe new parameter space, and that's not super deep. But the fact that you're doing muons can also reveal some new models. So something like an L mu minus L tau, which is just the lepton number of muons and taus, but then you gauge it, so you have this U1 boson. If you do something like that, then I mean, everything is just basically completely unconstrained because we have never had a collider source of second generation particles. So in a case like this, having the muon is important, and in a case like this, having the energy is important. Okay, and then I'll just rush through kind of the last few plots. Again, anytime that you have muon Philip couplings, things are pretty unconstrained, and you can push into this regime that people haven't been able to explore. A Higgs threshold is not a super promising option, but you know, even with something like a few tens of GeV on something very well explored like a dark photon model, you can still hope to make some progress. If you're only thinking about sort of order of a couple GeV, then something that people might want to do is this idea of a muon storage ring. And the idea is that you have this oblong thing, and when muons are decaying in these straight regions, you have a very collimated neutrino beam. So if you want to do short baseline experiments with neutrinos that are at a more precise momentum measurement than is previously done, then something like this would be really advantageous. So having these low energy muons, this neutrino factory idea, is what people might be interested in. And yeah, if you're going down to really low energies, basically the only things that haven't been completely excluded are things that specifically couple only to muons, and you can decide if that's a particularly motivated or relevant model. Okay. And then just a note about what we can do hopefully immediately. So sorry, Gardner brought up this point about colliding mu pluses. This is something they're very seriously considering at the JPark lab in Japan. There's other places both in Europe and the US, like Fermilab and PSI, that have dedicated neutrino programs. And the thing is, when you have a neutrino, they usually come with muons too. So there's a lot of underutilized low energy muon physics that's happening throughout the world because we're investing so heavily in neutrino physics. So studying muon forces or how muons behave or how to accelerate them could be done synergistically with any of these labs too. Okay, so sorry for being a little over time, but let's conclude. So basically my thesis about how we should approach the future of what collider to build next is by looking for the program that does kind of the most new stuff. A muon collider would be an amazing option, but it has to be tested, and it just doesn't seem impossible right now, but truly that story might change. Okay, since this is a long process, we should always be considering synergistic experimental programs to go with it, like this sort of beam dump facility side project. But really, we should think about all sorts of new physics opportunities that we can have if we have a machine in the future that's not only a precision, but also an energy frontier machine. So thank you so much.
And go back to the beam down and last slide.
Yeah, this one.
Yeah. Where do I get consistent? In the beginning, you said it's 10⁻⁶ of the original beam if I want to include nuance.
Oh.
I don't see a 10⁻⁶ number here in this.
Yeah, so that is, it's the 10⁻⁶ in phase space, not in number.
Okay. Do we know the flux reduction? Do we have an estimation of flux reduction?
So this is, yeah, this is roughly what Sergo told me, is that it's about a factor of 100 to 500, maybe more, is roughly what the flux reduction would be.
That's very nice. So it's much less reduction than.
I mean, if you talk to Scott Berg, then he'll be like, but you're always missing factors of 10 and 2 and those compound and blah, blah, blah. So it depends on which accelerator person you're talking to, how optimistic the projection is. But I think a factor of 1,000 would already be a conservative guess.
So the 500 is the 0.15%.
Yeah.
Yeah, go to your laptop box plot.
Yeah.
The field curves, I think.
Yeah.
That's the one, right?
Yeah.
So what is it, are you trying, you're doing off-shell precision tests? Is that what you're doing?
Yeah, so the idea is that if you have something like mu goes to BB, then the standard model background would be through Trillian or reverse Trillian if you want to be persnickety. And then the main way that you could test for it is from the interference term.
T-channel.
Yeah. So this is right. This is T channel, and then the standard model would be S channel. So then the primary way, because you have small coupling, but S channel suppression, so it's the interference term that's dominant.
And why does the pair production one goes up beyond the energy threshold? I would assume it's generally a vertical one. How come tilts to the right?
Yeah, I think the idea is that we let it, like, these don't have to be, we said that they don't have to be on shell. Because we define them by the final state, not necessarily, because there's no way that we could do this without having a well-defined final state. So the fact that it tails off a little bit below or beyond the the threshold of the kinematic threshold is because we're just saying that this should be to be final state rather than an on shell. But of course it's dominant when it's on shell.
Yeah, to be to left.
Yeah. Some muon colliders. Everyone's gonna go tell their congressperson.
I'm ready to buy your collider stocks.
Excellent. How about stickers? I can sell you stickers.
I already promised all my colleagues if they decide to build me a collider, I will devote 1 month of my time to shovel the ground.
I feel like there are better ways we could pay you in that month, Jen.
But by the time they start digging, it might not be.
You will not be able to
Real exercise.
Look, this is what Nima says every time I see him. The Muon Collider has given him a new lease on life. He wants diet and exercise and live to be 300 or whatever.
All right, let's thank Cari.